Rain.Water is a shader system for Blender 3D which adds rain and water effects to your materials and creates volumetric raindrops which synchronize and match with their corresponding splashes on rainwater surfaces. In this video you'll learn all there is to know about Rain.Water, the nodes that make up the system, how they work, and how to build rainwater materials both manually and automatically with the Rain.Water Manager. Rain.Water is only available from BlenderMarket, so once you've made your purchase, head over to your product download page on BlenderMarket and download the Rain.Water Manager.zip file, the Rain.Water version 2.1.blend file, and the Rain.Water 2.1 textures only folder if you're interested in seeing the demo scenes included in your downloaded blend file. You should unzip the Rain.Water Manager file with the extraction tool of your choice. Extract here. You'll get the Rain.Water Manager folder and inside the Rain.Water Manager.python file that we need. Now let's head over to Blender and we'll click on Edit, Preferences to open the Preferences editor. Select the add-ons category and click on Install. Now browse to the location of the Python files we just extracted. Select the Rain.Water Manager.py and click Install Add-on. The add-on has been installed and highlighted automatically for us. Now all that's left to do is for us to enable the add-on and we are ready to go. You can see that the Rain.Water submenu has appeared in the Materials tab of the Properties panel. And to start using the Rain.Water nodes, simply click on Import Rain.Water and now browse to the location of your downloaded blend file. Click on Import Rain.Water. And the nodes have been imported and we're ready to start building some materials. You'll see that the manager has been completed with several options, 3 couples of options, horizontal, vertical, and volumetrics, each with a bump and a displacement option. Now let's explore the options and see what they do. In this scene I have a plane which is 1 unit by 1 unit, so half the size of a default plane. I have a new material assigned, so I'll rename this material to water. And I'll use the Rain.Water Manager to add a horizontal bump setup. And now I can preview in Eevee, play the animation, and as easy as that, we have some water and some raindrops falling on top. Let's go a little further. I'll duplicate this plane and move it a little further along the Y and up along the Z by 0.1. I'll give it a new material. I'll call this one ground. I'll add another horizontal bump setup. But this time, I'm going to head over to the Shading tab, zoom in on my Rain.Water Ground node, and I'm going to raise the ground height input value to 0.1, the same value by which I raised the actual plane itself. Back to the default layout. And let's have a look. Now we've got our ripple rings and our droplet splats going on. Let's go further still. Duplicate the plane again. And this time I'll rotate the plane by 90 degrees along the x-axis. Move it back into place. Create another new material. This one I'll call wall. And I'll create a vertical bump setup. And just like that, we have a mini scene covered in rain. 1 water plane, 1 ground plane, and a window, I suppose you could call it. And now for some volumetrics. Let's add a cube and scale it to fit. To this cube, we'll assign yet another new material. We'll call this one volumetrics, and we'll add a volumetrics bump setup. Now to preview the volumetrics in Eevee, we need a lot of volumetric resolution, essentially as much as we can get. So tile size to 2 pixels and samples to the maximum of 256. And we can turn off volumetric lighting. We won't need it for this case. And for better Eevee previews, I recommend turning off viewport denoising, at least temporarily. Let's have a look from above. And there we have our volumetric raindrops. Let's see what they look like in cycles. And there you have it. Those are the 3 different types of rainwater material, at least as far as bump is concerned. But the rainwater effects really come into their own when they have some height information to work with. If you already have some displaced or modeled geometry, you can bake a height map from that geometry and feed the height map to the rainwater shaders. But as I'm working with flat planes for this example, I'm going to get my height maps from some PBR texture sets, which I'll download from polyhaven.com. If you want to follow along, head over to polyhaven.com, click on textures, and I'm going to do a search for some rocks textures. That's a good looking one right there, Aerial Rocks 2. I think I'll download that and see what it looks like. Over here in the top right, click on this menu button to open the menu of available texture types and make your choices. I have chosen AO, diffuse, displacement, and roughness, all in the ping format. And I've chosen a GL version of a normal map in EXR format. Click on download to get your textures in a zip file, and we can then unzip the file and import the textures into Blender. So let's head back over to Blender. I'm going to hide all this geometry in a new collection so I can start afresh. I'll add a new plane, scale it to 1 by 1, give it a new material, and now let's head over to the shading tab. We're going to drag in our textures, dragging them directly into the shader editor. I'll bring up a browser window. Here are my textures ready to be dragged in. And because I'll be using the manager to arrange these textures and build the materials, I literally don't even have to worry about where I place these textures. The manager will arrange them for me. So let's do just that. Head over to the Materials tab, the Rainwater submenu, and we'll build a horizontal displacement setup. To see the displacement in action, we'll need a lot of geometry to displace. So I'll come into edit mode and I'm going to subdivide my plane 10 times. And I'm then going to add a subsurface modifier set to simple with 4 levels for viewport, and I'll set render to 5 for that little bit of extra detail when it comes time to render. Let's have a preview and see what we've got. Cycles, we're ready to go. And there you can see your displacement happening. So we're off to a good start. You can come down here. This is your height map, your displacement texture. And this multiply node multiplies the output of that texture to control the amount of displacement that you actually get. You'll see that if I increase this value, currently set to 0.15, I can increase the displacement of the geometry from within the shader editor. Set that to 0.3, make it a little taller. And now I can come to the Rain.Water Ground node and increase my water height input value here. And there is the water we wanted. Let's come in closer and have a look at the animation. Obviously the animation will be somewhat jumpy in cycles, but you can clearly see the ripple effects, the ripple ring effects, the edges of the water where it meets the ground, the parallax effects, the discoloring, the darkening, and the sediments of the water, all visible. Let me show you a little better. I'll raise the water height. Come over to the Rain.Water Mix node, and you'll see we have some controls here: darkening, sediment color, and sediment intensity. Let me turn sediment intensity down to 0, so I can show you the darkening effect. By simply increasing this value, you'll see the blackness come in the deepest parts of the water, and this control very simply serves to darken the water the deeper it is. Similarly, the sediment intensity introduces the sediment color depending on the depth of the water. to create the illusion of floating sediments in the water, particles, dust, dirt, sand, and soil, and so on. I'll return that to the default of 1 for now. So that's how you achieve displacement in cycles. Eevee, however, does not have the luxury of material displacement, at least not yet. So we need to find some workarounds to make this work in Eevee. Let's have a look at that. We can't use the material displacement, so I'm going to disconnect this displacement noodle coming from the rainwater mix. It is no longer necessary. I already have a lot of subdivision on my plane, so a lot of geometry to work with. So I can come in and use a displacement modifier instead of material displacement. I'll have to create a new texture because I have no textures available. New texture, and click here to edit the texture. From the image settings submenu, I'll choose the aerial rocks displacement. There it is there, DISP, DISP. Now I can come back to the modifiers tab. Pay more attention to my displacement modifier. The texture is correctly set. The direction of the displacement along the normal will work perfectly well for our cases because our case is a flat plane. In other cases, you may have to set the direction to a global Z. But as I said, in our case, when we have a flat lying plane, it is exactly the same thing. The surface normal is Z in the global space. We'll set the texture coordinates to UV, the mid-level to 0, and I'm going to copy and paste my strength factor from the shader into the displacement modifier. Turn on smooth shading, and we're already looking good. Let's try an Eevee preview. We can see that we have the water effects, we have the displacement of the ground, but as I increase the water height, you'll see that while the water is being drawn in the material, the geometry is not being displaced to reflect the flat water level, and so things are looking a little strange. We have two options to introduce the water level in our Eevee displacement setup. Option number 1 is to modify or manipulate the texture that we use to control our displacement modifier. Come down to the colors section, and you'll notice that as I decrease the brightness input right here, the geometry starts to move downwards, and because clamp is turned on, when I reach a certain threshold, that threshold being 0, you'll see the geometry no longer gets moved downwards and begins to flatten out. So we can definitely take advantage of this to create our flattened water height, but taking a guess at the water height is not ideal, and luckily enough we already have the information to figure this out mathematically. What we have to do is to enter into this input field 1 minus the water height divided by the ground height. So I'll type in 1 minus 0.14 divided by 0.3, hit enter, and that is the correct displacement that you want. And now when you hit play, you'll see the animation playing much more smoothly, much more quickly, and it gives you a much better idea of what the final product will actually look like. All the other effects are still in place and working correctly. The only downside to this method is that you must constantly maintain this relationship between the brightness input of your texture and your water height and ground height in the shader. You could introduce connections through drivers, for example, but drivers will hinder your viewport performance no end, whereas here I'm getting 36, 37 FPS. When I add drivers, I reliably get about 7 or 8 FPS, so it's not ideal. But if that's something you're interested in doing, I'll show you how. Let's come over to the Modifiers tab. I'm going to look at the Displacement modifier, and we have a direct connection between the strength input of the displacement and this multiply node and its second input value. 0.3 is the value we want to enter into both of these input fields. So what I'm going to do is to right-click on this input field and copy as new driver. I'll now come over to the strength input field of the displacement modifier right-click on that field and paste driver. And as simple as that, I can now change the effects of my displacement modifier by changing the value here in my shader editor. This does not, however, affect the water level. So to introduce that effect, let's come back to the Textures tab. And if you remember, the equation for this value is 1 minus water height divided by ground height. So we're going to need our water height and ground height values, and we need to enter a lot of information into the equation which our driver is going to use, more than we can do by simply copying and pasting drivers. So we'll create a new driver, add driver or Control D. I'll now right-click again on the same field and open the driver's editor. Roll down the Textures tab right here and select the Brightness driver. Over in the Properties panel of the driver's window, right here under Driver, we have Scripted Expression, which will work for our needs. This is the expression which will be evaluated. We currently have our only variable, currently named var or var, plus 0.533. This is not what we'll be using in the end, but let's move a little further on and set up our variables. This variable I'm going to rename to WH for water height. I'm going to change the type to a single property. This property type will be a material. The material in question is my material, very aptly named. I'm going to rename that to ground. Bring my driver editor back, and I'll select the material named ground from the menu. And now here into path, I need to paste the data path of the input field that I wish to use. So I'll right-click on water height, click on copy data path, bring up my driver editor again, and with my mouse over the path input field, I'll press Ctrl and V to paste, and that is my variable correctly created. We need another one for ground height, exactly the same thing. I'll click on Add Input Variable. Set the type to single property. I'll call this one GH for ground height. The ID type to material. Choose the ground material. Come to the shader editor, right-click, copy data path, back to the driver editor, mouse over, Control-V to paste, and there we have it. Now, in the expression field, we'll type 1 minus WH divided by GH, enter, and we've got something very interesting going on over here. Let's have a look. I can increase the height of my ground, and we see that we are now leaving the water level behind as we scale the height of the ground up and down. By increasing the water level, we seem to be moving the ground upwards and downwards, which may not be what you expect. In this case, we might have expected the water level to rise while the ground stays still, and we can make that work, but we have to manipulate the mid-level of our displacement modifier over here. We're going to do that, believe it or not, with another driver. I'll add the driver and then open the editor. For this new driver, we can use the same variables that we created for our brightness driver. And luckily, we can copy and paste those variables by clicking here to copy. Now we'll come back to our mid-level driver. I'll clear this temporary variable because I don't need it and paste my new variables. There they are, water height and ground height. And now the expression is very simply minus water height divided by ground height. Enter. We've seen the ground jump upwards, so that looks promising. Reduce the water height, and the ground stays where it is. We can still reduce the height of the ground itself, and the water stays put. Now let's see what kind of damage we've done to our frame rate. If you remember before, we were around 36 to 37. Hit play, and we're getting about 8. As expected, but it certainly gives you a much better idea of what your material is looking like in the viewport before you get to the final render stage. And the second method for creating displacement using the water level in Eevee is to create a water plane. So let's see how that works. I'll head back to my default view and move this newly created plane into another new collection. So I can hide the collection and start afresh with a new plane scaled by half. Create a new material and head back to the shading tab. We can drag in our textures. But first, let's go get some new textures from Polyhaven. I'm going to stay with the rocks idea. This one looks promising as well. AO diffuse, displacement, EXR normal, and ping for roughness, all in order. Let's download and bring them into Blender. Here we are with our AO, diffuse, displacement, normals, and roughness. Subdivide our plane again 10 times with a subsurface modifier set to 4 for viewport and 5 for render, exactly like before. I'm going to set up the displacement like I did in the previous example. I'll choose my aerial rocks for displacement, and I'll set up my displacement modifier like I did before. I'll leave normal this time. UV texture coordinates, mid-level of 0, and a strength for now of 0 because I don't actually know what I want to set this to. I'll set it to something arbitrary. That'll do. Turn on smooth shading. And now to the materials tab, and we'll create a rainwater bump setup of the horizontal variety. Let's use an Eevee render. We'll turn on screen space reflections, and I also recommend for smooth and crisp viewport performance using Eevee with rainwater, turn off viewport denoising. We have created our ground plane. Let's create a water plane. We'll add a new plane, scale by half. I'll give it a new material called water. I already have a material called water. I'll call this one water plane. There we go. I'll need to use the same textures that I used for the ground arrangement. Drag them in as well. Horizontal bump setup. Now then, one more driver trick, which I'm going to use, is to use the world position, the Z position of this plane, as my water height, because this plane literally represents the surface of the water, so it is inextricably tied to the water height and should be correctly passed to the water plane and the ground plane materials. We'll do that by coming to the object properties, right-click on the Z component of the location, and copy as new driver. We'll now paste that into the water height input of the Rain.Water Ground node. Paste driver, and we'll do that for the water plane and for the ground plane. And now I can preview my plane. I can play, and you can see the raindrops falling on the dry ground, leaving behind splats. I can now literally grab the geometry of the water plane and raise it along the Z-axis. You'll see the water level rises correctly with it. We get wetness on the ground plane itself, and all the water effects are happening on the water plane. Darkening, sediment color, refraction. It's all going on. It's all happening in Eevee, and it's all happening real time. At 20 FPS, I happen to know I can do better than that. I can get at least 35, and I will do that by removing some extraneous functions of both the water and the ground materials. At this point, the water material will never need to adjust its specular, roughness, or IOR. It should represent all those values relative to water. So I'm going to disconnect all of those noodles and hard code the values into specular. I'm going to enter 0.255. Roughness will be 0.005, and the IOR will be 1.333. We also don't need the ground normal information. You'll never be able to see the ground on the water plane without water over the top, where the water normals will take precedence. I can mute this texture. Now let's have a look at the ground plane and see what we can improve. There are quite a few things to be removed here. We don't need the water normals coming from the rainwater mix, but we do want to keep the ground normals coming from the normal map texture right here. So instead of using the normal output of Rain.Water Mix, I'm going to drop in a standard normal map node, connect my normal map texture to the normal map node, and normal to normal of the principled shader. We also won't need the image texture coordinate distortion that the Rain.Water Ground introduces to create the parallax effects and the refraction effects. So we can plug all of these texture coordinates directly into our UV map node here. And the Rain.Water Ground node at this point no longer needs any texture coordinates at all, so I can sever that noodle. Now let's see how we're doing in terms of performance. We've gone up to 2930. Not quite as much as I wanted, but definitely an improvement over how things were before. And there you go. Those are the two methods for using Eevee along with displacement and maintaining all your rainwater effects with good performance in viewport. But we've done all this building of rainwater materials using the Rain.Water Manager, which has certainly given us something of an idea of how a rainwater material gets built. But now I'm going to show you how to build those materials by hand. I'm going to head back over to default and hide these planes away in yet another new collection. And hide it. I'll create a new plane yet again, scale it by half. And now I'll create some new materials with some new textures. Now I have already downloaded my textures if you're interested. I'll be using Cobblestone Floor 8 and Brick Wall 001, both from Polyhaven as before. New material, and head over to the shader editor. We'll drag in our textures. And this time, because we're building manually, we have to pay a little attention to where we actually lay the textures out. The most important one is the displacement or the height texture, this one. You should set that one apart, slightly off to the left. These ones will stay bunched up together because we'll be using them in one neat little group. So I'll stack them all one on top of the other. We have to pay attention to the color space for the roughness and the normal textures. I'm going to set the roughness texture to non-color, and usually with a ping normal map, I would set it also to non-color. But because I imported my normal map as an EXR format, Blender has automatically correctly set it to linear for me. So as far as the normal map is concerned, I am ready to go. This is how I set up my PBR setups. The diffuse and the AO get mixed with a color multiply node. Separate the color output of the roughness texture with a separate RGB node. And it's also important to set the height map or the displacement map to a non-color color space. Now then, every rainwater surface material will have two nodes. The Rain.Water Mix node and either a Rain.Water Ground or a Rain.Water Wall node, depending on whether or not we're making a horizontal or a vertical setup. In this case, it is a horizontal setup, so I'll use Rain.Water Ground. The Mix node I will leave here between the textures and the principled shader. I'll hook it directly to the principled shader. Now the color textures go into the color input of the Mix node. One of the color channels of the roughness color output, which has been separated, goes into the roughness. And the result of our normal map texture goes into the normal input of the Mix node. Very simple. Now to connect the two rainwater nodes together, it's mask data to mask data and height data to height data. Very simple. That's how the rainwater nodes communicate, and that's all we need to do to them for now. We'll use the text coordinates output of the Rain.Water Ground as texture coordinates for these textures. The height map texture instead gets its own UV map. I'll separate the colors as I did for roughness. and I'll give it a multiply node so we have some control over the displacement, the actual height of the displacement. A good default value for a height map that I've come to use over the years happens to be 0.15, so I'll go with that for now, but it's very easily changed at a later date. The Rain.Water Ground node also needs a UV map, or some kind of texture coordinates. In this example, I'll be using a UV map. And it also needs time in seconds. Now, there are a few ways you could do that. You could do it with a keyframe. You could do it with a driver. That's how I choose to do it. I use a value input node. And into the value input node, I type hash frame. And this gives me a numerical representation of the current frame of my blend file. You'll see that as I play, that number increases. Frame 103, 103 in my value input. That makes sense. So I can divide that number by the frame rate of my blend file. Let's check it. It's 60 FPS. I'll divide by 60, and the output of this node now gives me the time of my animation in seconds, very simply. Connect that to time. We'll connect our height texture here to the ground height input of the Rain.Water Ground node. And that is your rainwater material finished and ready to go. Let's have a look. And there it is. We can see our rain droplets, or splats as they're known, on the dry ground. And now I can increase the water height. There's our water coming in, taking over the stones. Let's have a look at the sizes of the effects. These rain effects look a little small for this texture. The Rain.Water Ground node inputs are as follows. Time, ground height, and water height we have already seen. Ripple height. Let me increase the water height to show you what that does. Literally increases the size of the bump of the surface ripples. Usually this will be set to a very small value, in this case 0.005, which is the default. I can increase that a little bit. You can see the water gets more turbulent on the surface. And that is ripple height. Ripple height is also tied to the height of the edges, which we'll see in just a second. So keep that in mind for later. FX size controls the actual size of the rain effects, the rain ripple rings, the splats on dry ground, and so on. You'll see as I increase this value, the rings increase in size and also seem to become more densely packed with rings, so to speak. And that's because we have increased the size of the simulation, but we also have the precise and direct control over the size of the rings, or the frequency of the rings, more to the point. In fact, if I drag this node out, you'll see this input is called ring frequency, currently set to 500. I can reduce that value, and you'll see that the ripple rings get larger and we see fewer of them, hence they are less frequent. You can still play to see what they look like. We also have control over the ring fall off. As I increase this, you'll see that we get more rings on the inside, at the center of our ripples. This essentially controls how quickly the ripples die out as they move away from their origin point. Now to see the edges, I'm going to reduce the water height. So we can see the water at the edges of the ground, where the ground is higher than the water. And you can see this rippling distortion going on at the edges right there. Let me reduce the water a little bit more, possibly see it better. Okay, there's a good look. And we have similar controls to the controls we have over the ripple rings, over the edge ripples. We have edge frequency, which, like the ripples, simply increases or decreases the number of ripples that happen in any instance of the effect. Fewer instances also make for larger instances, so keep that in mind. Fall off, exactly the same as the fall off for the ripple rings. The larger fall off means the edge ripples extend much further into the water, and 0 makes them non-existent. And finally, we have control over the speed of the animation of the edge ripples. Those are the controls of the Rain.Water Ground node. It's as simple as that. You can keyframe them, you can use drivers on them, you can input them directly, you can click and drag, you can type in numerically. The choice is yours. Rain.Water Mix essentially takes the majority of its important information from the rainwater generator node, be it ground or wall. The controls that we have, as we've already seen, are darkening and sediment intensity. I can turn that up to see some sedimentation in this water. And here I can change the color of my sedimentation, should I see fit. Roughness will generally take its information from a texture, as in this case, but there's nothing to say you can't input the value directly and just leave it as a hard-coded value. Possibly the material will be less interesting, but it depends entirely on your use case. IOR is the index of refraction of the surface underneath the water. This is not the water IOR. That is provided automatically by the mix node. And the normal input will usually be left unused like this, or will take a normal texture input. That is how you build a Rain.Water Ground node by hand. Now let's have a quick look at building a vertical setup or a wall. I'll create a new plane, same as before, scale it. We'll give it a new material and drag in our textures. This time I'm going to use the brick wall textures, as I mentioned before, brick wall 001. Drag in my albedo AO, displacement over to the left, normal map down the bottom, and roughness right here. Let's line them all up, make them nice and tidy and pleasant to work with. Change the color space as necessary. Roughness must be non-color. Normals is correct. Displacement must also be non-color. Once again, I'll use a mix RGB set to multiply for my albedo and AO. I'm going to move all these textures over a little bit so I have room for my Rain.Water Mix node. Hook it up to my principled shader and plug my color result into the color input. Another separate RGB node for my roughness so I can use one channel, and my normal map straight into the normals of the mix node. I'll give my displacement texture a UV map, split apart its components, and control one of those components with a multiply node, just like before. Set to my usual default of 0.15 temporarily. This is a brick wall, so I'll probably have to reduce that. Let's add the rainwater generator node, which in this case is a wall node. I'll expand it a little bit so we can see all the inputs. Just like before, we need FX coordinates. I'll use a UV map. We need time in seconds. I'll use a value. Hash frame, plugged into a math node set to divide by our frame rate of 60. That goes to the time input. Now here's the first difference, the first major difference at least, between the ground node and the wall node. You'll see that here we have a roughness input. So we got to move our roughness texture from over here to sit alongside our displacement texture and use the same UV map so that we can feed the roughness into the wall node. Let me change the order of these textures because the height input goes in below roughness. So for tidiness sake, let's keep things orderly. FX size, I changed that previously in my ground setup to 0.09. So I'll enter that here as well. Mask data, height data, and roughness all go to my Rain.Water Mix node. And that means that my textures here need a UV map node. And with that, we should have a good preview to check out. Looking pretty good. Animating well, we've got good looking droplets. We still got our splashes, splats, and ripple rings down here. And we're getting 26 FPS in viewport, not bad at all. Let's have a quick look at the Rain.Water Wall settings. As before, we have FX size, works exactly like the ground node. We have a general wetness input for the wall. Very simply makes everything wet. There's no bump or effects of any kind. It just simply makes the surfaces wet and shiny. We have intensity for splats, noise for splats, and the same intensity and noise for droplets. So what is the difference between a splat and a droplet? With the animation playing, I can turn droplets intensity down to see only the splats. And I can then remove the splats and reintroduce the droplets, and you'll see that the droplets are the ones that are animated. They fall downwards along the surface, whereas the splats happily sit there for a second and then get absorbed into the material while spreading their wetness outwards in a very nice patch. Let me pause for a second so you can better see the noise controls. If I turn the noise down to 0, you'll see the droplets and the splats are perfectly circular, and a little noise to make them much more irregular and much more natural looking. An intensity of 0.5 should work. I'll bring my droplets back in. Actually, let me remove the splats so you can clearly see the effects of the inputs on the droplets. Droplet noise distorts them, predominantly along the horizontal axis. Droplet max length and min length now. The droplets are drawn at a randomly chosen length. Some of them are a lot longer than others to really help the natural chaotic illusion of the nature of rain. If I set both of these settings, both minimum and maximum, to 1, then all of my droplets will have a length of 1, or top to bottom using the entirety of my UV map. If I leave the max at 1 and set the minimum to 0.5, I'm getting droplets of variable length of anything between half of my UV map and the entirety of my UV map. In this example, I have 14 bricks. So if I set a minimum length of 1 divided by 14, that gives me 0.072 rounding up. So I'll enter double of that into the maximum input. Droplets running across multiple brick faces does look a little strange, but I think adds to the chaotic nature. So I'm going to increase the maximum length. 0.3, for example. I'm going to make them longer still, 0.5. There we go. Now we got a little bit of everything, some very small ones and some significantly longer ones. And that is the Rain.Water Wall node in its entirety. And this is a good example of what a hand-built Rain.Water Wall material should look like. The third and final generator component of the rainwater system is the volumetrics node. So let's hide away these planes in a new collection. And let's get ourselves a cube so we can see some volume. I'm going to head over to the shader editor. We'll give our cube a new material and I'll rename it to Volumetric Rain. And I'll add a Rain.Water Volumetrics node, small and unassuming though it is. I'll open the node out so we can see the inputs. We have domain height, which is literally the height of the cube, the volume which will represent our volumetrics. We're familiar with the time input. This expects the time of the animation in seconds. FX size we've seen before. Droplet length and radius we'll see once we can see our droplets. And ground height and water height we only need to worry about if we're going to be using the displaced output. I'm going to use the flat output for now. So let's begin by giving our node the domain height. You can find the height of your domain, of your volume, In the N panel under Dimensions, check the Z size. In our case, it is 2. So I'll enter 2 for domain height. I'll use my usual hash frame driver, followed by a math node dividing by the frame rate of my animation, which is 60 FPS, connected to time, ready to go. I'll set the FX size to 0.1 arbitrarily for demonstration purposes. And now, what do we do with the output of our volumetrics? First thing, we need a principled volumetrics shader, principled volume shader. Let's get a look at what we've got. I'm going to use cycles for this demonstration. And there we have our volumetric cube. Now I'll set the density to 0. And I'll use the flat output of my Rain.Water Volumetrics node to control the emission strength. Drop in a math node set to multiply, and we can control the strength of the emission with this node here. As I increase, you'll see the droplets start to come in. Usually a value of around 30 or so should give us a good result. There you can see the droplets. Let me highlight the cube so you can see the boundaries. And now I can play, and you can make out the droplets falling downwards. If I zoom into the cube, so we're inside the volume, and look upwards, you can more clearly see the droplets falling downwards directly towards the camera. And with that, our volumetrics are working. The way the volumetrics node works is by animating the raindrops to fall from the top of the volume to the bottom of the volume in 1 second. So the taller the volume, the faster the droplets will fall. Obviously, as you stretch the volume, the droplets get stretched as well, and you can compensate for that by adjusting the droplet length input. Furthermore, to change the apparent density of the raindrops, this looks like a very heavy rainfall. You can increase the FX size, which will increase the size of the pseudo simulation of the shaders, which certainly reduces the density of the raindrops, but it also increases the radius of the raindrops, making each individual one thicker. And luckily we can compensate for that as well with the droplet radius control right here. I'll reset these to defaults. Scale my cube down a little bit, and I'm going to realign the bottom of my volume with the 0 of the Z coordinate of the world, like that. And that will ensure alignment and correct timing between the volumetric raindrops and the splashes and splats of a piece of ground geometry using a Rain.Water Ground node. Let me show you that. I'll temporarily hide the cube, create a new plane, and I'll use the manager with a new material to create a bump material. For the droplets and the splashes to match up, the settings on the Rain.Water Ground node and on the Rain.Water Volumetrics node must match. So for my volumetrics, I have an FX size of 0.41. I'll enter that into my ground node, FX size 0.41. And now if I view from above, which can make the raindrops much easier to see, these white dots are the volumetric raindrops falling towards the water. And here we can see the ripple rings. If I pick one which is close to impacting the water, this one for example, I'll now advance in frame slowly. And there are the ripple rings coming in just after the droplet impacts the ground level. And speaking of ground level, this ground level, as you'll notice, is flat, hence my use of the flat output of the volumetrics node. The displaced output exists because your ground will not always be a flat plane. It's much more likely that it will be displaced or modeled in some way. So we need to pass that height information to our volumetrics shader. First of all, let me displace this plane a little. I'll subdivide it by 10 and add a subdivision surface modifier set to simple with a viewport level of 4, render of 5. I'll add a displacement modifier and a new texture using the aerial rocks displacement from before. I'll use the UVs mid-level of 0 and a strength of 0.3, for example. That should work. No, I'm going to make that more intense, 0.5. Turn on smooth shading, and now let's enter that ground information to our node right here in ground height. We have two options now. We can use the same texture that we used for the displacement modifier, or we can tell the shader to simply check the height, the vertical height along the z-axis of the geometry, because this geometry is now displaced. We can do that with a texture input node. We'll use the object output, separate it with a separate XYZ node, and plug the Z component directly into ground height. That is the height information for the ground shader sorted. But to pass that information to our volumetrics is a little more complex. From the volumetrics, we no longer have access to the geometry of our ground, so we are forced to use the texture in this case. And things get even more interesting because we're using a texture, and a volumetric setup cannot use a UV map. A UV map only considers 2 coordinates, X and Y, whereas for volumetrics we need all 3. So I'm going to add an empty to my scene and use the empty as texture coordinates for the height texture, which I will read inside the volumetrics shader. I want my empty to be aligned with the bottom front left corner of my volume. So I'll select the bottom left and frontmost vertex and snap the cursor there. And now in object mode, I can create an empty at that point. And come back to my volumetric shader. I'll add a texture coordinates node, and I'll use this eyedropper to select my newly created empty. Now I can drop in the image texture node and select the aerial rocks displacement. I'll use the object output of the texture coordinate node. Create a little more space here because I need to separate the color of my texture, and then I'll need a multiply node to control the height. This value must match the height of the displacement modifier, which I set to 0.5. So I'll enter 0.5 and connect that to ground height. The water height in my ground shader is 0. I'm going to set it to -1, and I believe the volumetrics is already set as such. In fact, it is. So we should be good to go. Let's have a look. And now we're looking for splats appearing as the raindrops impact the ground. There's one. Here's another droplet coming down. Let's follow it. It has impacted the ground here. And there's its splat. We're still a little off, which makes me think I might not have used the displacement output of my volumetrics node. Let's have a look. In fact, there it is. Now, because I've scaled the size of my volume, I have to update the domain height of my Rain.Water Volumetrics node to 6.241. 6.241. And now we should hopefully see the raindrops impact the ground and leave behind a wetness splat where they touched. Let's follow this one. There's the splat. Let's zoom out a little more. Let's follow this one the whole way down if we can. I'm going to have to zoom in to keep up with it. It's this one here. Advancing in frames. There's the impact, and there's the splat perfectly in time. And that is how you synchronize your droplets and your rainwater effects on the ground geometry, both in terms of alignment in X and Y, and the timing alignment along the Z-axis.